All scientific measurements are uncertain. This is because measurements are inherently subject to limited accuracy, limited precision, and may contain a degree of bias. In this video, we use the significant figures convention to show how we quantify the level of uncertainty in scientific measurements. Here we have our paperclip from previous videos, which we have measured to be 3.5 centimeters in length. The measurement has uncertainty associated with it because of the limitations of the ruler's scale, which has divisions set at 1 centimeter apart. Using this ruler, we can be very confident that the paperclip is between 3 centimeters in length and 4 centimeters in length. But in order to achieve a more accurate reading, we have to make an estimate between these two values. In general, we should estimate measurements to within 1/10 of the smallest scale division of the instrument we are using. Hence, in this case, we estimate the length to be 3.5 centimeters, with the 0.5 being a guess to the nearest tenth of a centimeter. Of course, this value has a level of uncertainty about it, and a simple way of indicating the level of uncertainty is to report the result so that it contains only a certain number of digits or figures in the value, known as significant figures. And scientists typically report all the figures they know for certain, plus one extra figure that is uncertain. So in this particular measurement, the 3 is considered certain, and the 5 is a bit of an estimate and is considered uncertain. Now, if we use a different measuring system, in this case a different ruler, to measure the paperclip, we may be able to be more certain of its length, and therefore we may be able to report the result with a greater number of significant figures. The more significant figures a measured value has, the greater the certainty associated with its measurement. In this diagram, the ruler now has scale divisions set 0.1 centimeters apart. We can now be more certain about the measurement by recognizing that the true value of the length of the paperclip lies between 3.4 and 3.5 centimeters, and estimating between these numbers, we can report the length to be approximately 3.46 centimeters. In this case, the 3 and the 4 are certain, and the 6 is uncertain. So in this first scenario, we could only be certain of the figure 3, and we reported one uncertain figure, the 5, which we estimated. This measurement, 3.5 centimeters, is said to have 2 significant figures, and is less certain than the measurement on the right, which has 3 significant figures. Here we have a pencil that has been measured rather accurately with a very sensitive high-resolution measuring device to have a length of 9.1080 centimeters. Now, when we see a measured value written like this, how do we know how many significant figures this measured value actually has? This is important because the number of significant figures a measured value contains tells us how certain we are of that measured quantity. For example, I'm going to tell you that this measured quantity of 9.1080 centimeters is known with a greater certainty than a measurement of 9.1 centimeters, where the measurement has been made in a different way using a different measuring device. The way we determine how many significant figures this measurement has is to follow a few simple rules. The first rule is to disregard all initial zeros in the magnitude of the measured quantity. Second, we're going to disregard all terminal or end zeros unless they follow a decimal point. Third, all remaining digits, including middle zeros, are significant. The measured value for this pencil on the right-hand side, therefore, has 5 significant figures in it, and in this particular case, all 5 digits are significant. There are no initial zeros in this example, so Rule 1 does not apply. There is a terminal or end zero, but it comes after the decimal point. So that terminal zero is going to be a significant figure in this measured value. All other remaining digits, including the middle zero, are significant figures in this value. So we start counting here, and we end counting here, and we get 5 significant figures in this measured value. Now, of course, we know that we can represent this measured value of 9.1080 centimeters as 0.91080 decimeters, or 0.091080 meters, or even 0.00009180 kilometers. And all we are doing here is changing the prefix in front of the unit. We're not actually changing the way that we measure the length of the pencil. So therefore, we should not be changing the certainty of the measurement. In other words, representing the length of the pencil in these other ways should not change the number of significant figures. And when we apply Rule 1, we see that this is indeed the case. In the second value, you can see we have an initial 0. In the third value, you can see we have 2 initial zeros. And in the fourth value, you can see we have 5 initial zeros. We're going to ignore all these initial zeros and start counting from the first non-zero digit. And so we've got 5 significant figures there, 5 there, 5 there, and 5 there. So all of these numbers have 5 significant figures. And that is appropriate because, as I said, all we are changing is the prefix. We are not changing the way that the measurement was carried out, and therefore we shouldn't be changing the uncertainty involved. And just remember, this 0 here, even though it comes after a decimal point, is still an initial 0. And these 4 zeros here, even though they come after a decimal point, are still initial zeros. And so we don't start counting until we get to the first non-zero digit. We also know that 9.1080 centimetres can also be expressed as 91.080 millimetres, or 91,080 micrometres, or 91,080,000 nanometres. And again, all we are doing here is changing the prefix of the unit. We are not changing the way the measurement was carried out, and therefore we shouldn't be changing the uncertainty of the measurement. In the top value, we have an end or terminal 0 here, but it comes after a decimal point, so this 0 is still a significant part of the number. There is an end or terminal 0 in this second value, but again it comes after a decimal point, so it's fine, it's a significant part of the number. Those first 2 values have 5 significant figures in them. But in the third value, we have a terminal 0 that doesn't come after a decimal point. And in the fourth value, we have 4 terminal zeros that don't come after a decimal point. So in these 2 measured quantities here, do we have only 4 significant figures represented by the green lines? Now, one would hope not, because again, I would stress that we haven't changed the way we made the measurement. Therefore, we haven't changed the uncertainty. And so what we see now is confusion arising when you have terminal zeros not after a decimal point. One way to avoid any confusion is to express this value here of 9.1080 centimetres in terms of scientific notation. So if we wanted to keep centimetres as a unit, we represent this measurement as 9.1080 times 10 to the 0 centimetres. 10 to the 0 has the value of 1, so we're just multiplying by 1. So that still keeps it as 9.1080 centimetres. If, however, we want to represent this measurement in millimetres, 91.080 millimetres is best represented in scientific notation as 9.1080 times 10 to the 1. 10 to the 1 has the value of 10, so multiplying by 10, we regenerate our original number of 91.080 millimetres. If we want to represent this measurement in micrometres, 91,080 micrometres is best represented in scientific notation as 9.1080 times 10 to the 4. 10 to the 4 has the value of 10,000, and so multiplying by 10,000, we regenerate our original number of 91,080 micrometres. And finally, if we wanted to represent our measurement in nanometres, 91,080,000 nanometres is best expressed in scientific notation as 9.1080 times 10 to the 7 nanometres, and the 10 to the 7 has a value of 10 million, so multiplying by the coefficient by 10 million, we regenerate our original number of 91,080,000 nanometres. All of these numbers are expressed in scientific notation, and all of them have 5 significant figures. Expressing these measured values in scientific notation removes any ambiguity or confusion about end or terminal zeros, because you simply count up how many digits or figures are in the coefficient of the number written in scientific notation. So if you see a measured value written in scientific notation, simply count up the numbers in the coefficient and you'll have the numbers of significant figures. And that's why it's also best to record your measurements in scientific notation so that it will be unambiguous to others about how many significant figures you have in your measured value. So we've seen expressing scientific notation with positive values of the exponent is the right way to go. It's also the right way to go with negative values for the exponent. So 0.9108 decimeters is best expressed as 9.1080 times 10 to the minus 1 decimeters. Similarly, 0.091080 meters is best expressed in scientific notation as 9.1080 by 10 to the minus 2 meters. And 0.000091080 kilometers is best expressed as 9.1080 by 10 to the minus 5 kilometers. Again, all are written in scientific notation, all with the same coefficient, and all those values have 5 significant figures.